In the first video on oscillatory motion, we looked at the displacement of an oscillating object and derived a formula to describe its displacement from its equilibrium position. This formula is the amplitude of the oscillation, or its maximum displacement, multiplied by the cosine of the angular frequency and time. In this video, we will derive its velocity and acceleration. Now that we have the displacement equation, we can determine the velocity of the oscillation because we have defined velocity to be the rate of change of displacement with respect to time. So the oscillator's velocity is found by taking the derivative of the displacement equation. The derivative of a cosine is a negative sine. So the velocity of an oscillator is equal to minus omega a times the sine of omega t. With some mathematical manipulation, the velocity can be written more simply as omega times the square root of the amplitude squared minus the displacement squared. Now let's have a look at the velocity characteristics in more detail. When we pull the mass to its maximum displacement and hold it, its initial velocity is zero. As soon as we let it go, it starts to move upwards. As it moves to its central equilibrium position, it increases in speed, as indicated by the growing blue vector arrow. At the same time, the displacement vector, indicated by the red arrow, is decreasing as the mass moves closer towards equilibrium. At equilibrium, the velocity is at its maximum and the displacement is zero. As the mass continues to move upwards, past equilibrium, it begins to slow down, eventually coming to a stop at the maximum positive displacement, or the maximum amplitude. At the same time, the displacement vector increases up to the maximum amplitude. So displacement and velocity are out of phase with each other by 1/4 of a cycle. When velocity is at a maximum, displacement is zero and vice versa. This is reflected in the velocity and displacement equations, where one is a cosine and the other is a sine, and the difference between them is 1/4 of a cycle, or half pi radian. Where is the velocity maximum and displacement zero? Now let's have a look at the acceleration of the oscillator. Acceleration is defined as the rate of change of velocity, so we can derive the acceleration equation by taking the derivative of the velocity equation. The derivative of a sine is a cosine, so the acceleration of an oscillator is equal to negative omega squared times the amplitude times the cosine of omega t. Since the displacement is equal to the amplitude times the cosine of omega t, then acceleration can be written as negative omega squared times the displacement. So we can see that acceleration and velocity are out of phase with each other by 1/4 of a cycle. And since velocity is out of phase with displacement by 1/4 of a cycle, then acceleration is out of phase with displacement by half of a cycle. This is evident in the negative sign of the acceleration equation. So acceleration is a maximum when displacement is a maximum, and acceleration is zero when displacement is zero. But the acceleration vector, shown in the black arrow, always points in the opposite direction as the displacement vector. The acceleration vector always points towards equilibrium, while the displacement vector always points away. This is a consequence of the third characteristic of harmonic motion, which is a restoring force being proportional to the displacement. Newton's second law tells us that force is equal to the product of its mass and its acceleration. The oscillator's acceleration always points inwards and is a consequence of a force that tries to bring the mass back to its equilibrium position, hence the term the restoring force. This is known as Hooke's law, which will be the topic of the next video. The displacement, velocity, and acceleration of the oscillation can be described by trigonometric means because of its periodic motion. When displacement is described by a cosine function, then velocity is given by its derivative, which is a sine function. Acceleration is the derivative of velocity, so is described by a cosine function. Velocity is out of phase with displacement by 1/4 of a cycle, while acceleration is out of phase with the velocity by 1/4 of a cycle, which means acceleration is out of phase with displacement by half of a cycle. The acceleration vector always points towards the equilibrium position and gives rise to the restoring force that is characteristic of elastic materials.